Hello, everyone. My name is Ghena Barakat, and I'm so happy to be with you today and to discuss our work, discrete event modeling and simulation approaches for industrial Internet of Things. We will start our presentation by a brief introduction about the work in general, followed by some challenges that may face the industrial Internet of Things devices. Then we will talk about the idea of using simulators or the simulation process in such a field of research. After that, we will be comparing this simulator, or we will be comparing between the three simulators that can be used for modeling and simulation IIoT devices. Then we will discuss the devs for IIoT security and operations, followed by a case study to detail how we can use this kind of simulator in modeling and simulation for industrial systems. After that, we will conclude our work and we will discuss also some of the ideas that can be added to this kind of research to improve it in the future work field. Starting by introduction. Okay, now the discrete event system specification, or what we can call it DIVS, is considered to be a modeling and simulation environment which can be used to model the desired systems, whether these systems are discrete or continuous, and then simulate these systems under the DIVS simulation environment. Now, we will be using this simulator in our work to model and simulate IIoT systems, where we can define the IIoT devices in general as the integrating of internet connected devices, sensors, and machinery with industrial settings to enable a real-time data collection, to monitor and to analyze across interconnected machines and systems, where we can improve by this the operational efficiency, we can enhance the productivity of our systems, and we can optimize the decision-making process. Now, the IIoT is considered to be one of the main parts in the Industry 4.0, where we can define the Industry 4.0 as the integrating of advanced digital technologies into manufacturing and industrial process to create the smart factories. These smart factories considered to be highly efficient, flexible, and data-driven, and will enable a real-time decision-making, will enhance the productivity of our systems, as well as the ability will increase the ability to customize the production. Now, some of the challenges that may face the IIoT devices is the security threats, like the brute forcing, the malware, the remote code executions. Such kind of threats will cause potential operational disruptions, will cause data breaches and system compromises. And also, the implementation complexity is considered to be one of the main challenges that may face the IIoT because of the high cost and operational inefficiencies in deploying larger scale systems. Why the simulation in this field? Why we are heading to use a simulation, the idea of the simulation? Because the testing of real world IIoT systems considered to be very expensive, very complex, and also because the simulation will offer a cost effective, flexible environment for experimentations. Also, the approach behind DIVS is that it is a mathematical modeling framework for both discrete and continuous systems. And this simulator, or this environment, is considered to be a scalable, flexible, and real-time behavior analysis. So because of all these advantages for such an approach or such an environment, led us to think, why not using the simulation in this field, and why not minimizing the challenges we can face comparing to deploying the systems on real life. Okay. Here we are going to start a comparison between different kind of simulators, where as you can see, these are the features we used to compare between these three simulators. Let's take the scalability as an example. DIVS is considered to be a high scalable environment comparing to the IoT NetSim, but also the FS IIoT SIM simulator is also considered to be high. But if you can or as you can see here, and what's based on what's included in the table, based on the research we've done before, we can see that devs can handle large complex systems with modular decomposition very easily, while the FSIIoT SIM, it's true that it can scale large networks, but set up for such systems or such networks is considered to be time consuming. So devs is more scalable comparing the other two simulators with less limitations from this side. Also, for example, let's take the integration with other tools, as we can see in this table, or as we mentioned in this table. Using devs with other tools is can be a very easy process, especially that devs is considered to be standardized formalism and allow easy integration with other tools. Comparing to the other two simulators, where integrating them to other tools is a limited process, and it's considered to be one of the challenges to integrate new tools due to the system architecture that the environment provide. Okay. Now, we can use devs for security modeling, where we can simulate the scenarios like botnet, like data manipulation, like replay attacks, and we can analyze the system resilience and failure conditions as well. It also provides us with the ability for real-time simulations, where models real-time interaction. It can provide a real-time interaction between system components, and it can enable the performance optimization and risk management. Now, to make the things more clear for you, we have this case study where we suggested that any factory or any system, complex systems, consist of simple systems, where in the simple systems we have three main components interacting with each other. We have the sensor, we have the PLC, we have the actuator. Now, the sensor will be in one of three states at a time, where it will start with ideal state. Ideal state, the sensor is doing nothing and waiting for an order to start sensing and preparing the data to be sent for the PLC. Once we have this trigger that enables the sensor to start sensing the data, it will change its states to the monitoring state. Will start sensing and collecting the data and prepare it to be sent to the PLC. Now, when it will be sent to the PLC, or when it can send the alert to the PLC, when it finish the monitoring process and move on to the active process. From active, if there's other data to be to sense again, it will come back to the monitoring state. Otherwise, if it finished sensing, it will go back to the ideal state. Now, once the alert is being sent to the PLC will receive this alert, and in this case, it will change its state from the ideal to the processing state, where in this state it will start processing the received alert and preparing the command based on what data it receives from the sensor. And once the command is ready and the processing is finished, it will move to the send command state. Once the command is being sent from the PLC to the actuator, it will come back to the ideal state and wait for other data to be received from the sensor. Now the actuator, when it receives the command that being sent by the PLC, it will change its state from the ideal. Ideal means doing nothing and waiting for a command to be received, to the active. The active will start do what it has received in the command in the active state. Once it finish doing the order it received by the PLC, it will wait for other commands to be received from the PLC. Now, the system we discussed, or the case study we discussed before, we built it using the environment, the devs environment, as this. So the system overall, after we build each one of the models alone and connecting them all together, will be just like this. Here we have the PLC. We build it as one separate model, and it's called the atomic model. As you can see here, we have the import. Here we the output that is being used to send the command to the actuator. Same thing for the actuator. It has the import to receive the command. It has an output to send a message in case of failure for the sensor. The sensor, it has the failure import where it can receive a message from the actuator if there is an issue in the command being sent by the PLC. And we have the start monitoring import, the trigger that will enable the sensor to start sensing the data. Here, the letter we can see in the blue inside each one of the boxes shown in this image is or represent the state this model is now. So all of them now in the ideal state because we did not start the process yet. So this is the whole system after building it on the simulator, and this how it will be. So we have three main components, three main models. After we finish building each one alone, we connect them all together to have the complete system, as we can see. Now, in the complex system, since we build, we said one of the advantages for the DIPS is that we can break down the complex systems into small parts, and building these small parts will enable us later on to connect them all together and have the whole system or the complex system. Here, this what we have done in the previous in the previous slide, sorry, we build the simple system that consists of three main atomic models, and we connect them as the case study shows exactly. And in the complex system, what we have done is having one PLC, we have 10 sensors, and we can have more. We have 10 actuators, and also we can have more. From the sensor model, we built 10 copies. Each copy has its number to show that it represents a different sensor. Each one of these sensors can send the data being sent to the PLC. So in this case, we can the PLC can receive 10 data or 10 messages from 10 sensors at the same time. And when receiving these data, it will store them in a queue where the first one is received, the first one is being processed, and the first one is being sent to the related actuator. For example, sensor number 9, when it sends a message to the PLC, this message, after being processed here in the PLC unit, it will be sent to the actuator number 9. and so on. If we have sensor 3, sensor 4, sensor 5 sending messages to PLC, we will have 3 messages from sensor 3, 4, and 5. So the first message, sensor 3, if it received at first, it will be sent to the actuator 3. The second message, it will be sent to the actuator 4. The third message, it will be sent to actuator 5. Now, we can conclude that devs offer a scalable, flexible, and security-focused simulation approaches for IIoT systems. The benefits of using this simulator is to help in identifying and mitigation risks that may occur in any system, to optimize the system performance and resilience. Now, what we can add to this work to improve it more and to show the potential of using this simulator in such field of research. Now, incorporating advanced real-time monitoring and cybersecurity scenarios to address Industry 4.0 challenges will be one of the ideas we can add or we can improve to on this work. This is all. Thank you.